binomial series as power series. In this section we will learn that how to represent binomial series as a power series. How we can do this? We're going to represent the binomial series as a power series. So let's do some examples. Example number 1. Represent the expression 1 plus x to the negative 2 as a power series. As I told you, in this section we're going to learn that how to represent binomial series as a power series. Here the binomial expression has been given, which is 1 plus x to the negative 2. How are we going to represent this binomial expression in terms of power series? So first we need to expand this binomial series. After expansion at the end, we're going to do its match with the power series to represent it as a power series. First we need to expand the series. So we're going to use the binomial theorem here. We want to expand it first with the help of the binomial theorem. So we know that the given expression is 1 plus x to the negative 2. So according to the binomial theorem, I will have 1 plus x to the negative 2 equals to 1 to the negative 2 times x to the 0 plus negative 2 times 1 to the negative 2 negative 1 times x to the 1 plus negative 2 into negative 2 negative 1 over 2 factorial times 1 to the negative 2 negative 2 times x to the 2 plus negative 2 into negative 2 negative 1 into negative 2 negative 2 over 3 factorial times 1 to the negative 2 negative 3 times x to the 3 plus infinity. Remember, don't forget this infinity. It goes to infinity because the power n is in negative form. If the power n is in negative form or in fractional form, then we have infinite binomial series. Binomial series with a negative power or with a fractional power, it goes to infinity. So don't forget it goes to infinity. You can add more terms if you want, but I just chose the first 4 terms, 1, 2, 3 and 4. You can add more terms if you want, which equals to 1 minus 2x plus 3x squared minus 4x cubed plus infinity. Just do simplification on the right side, you will get this expression. Now this is the final expansion of the binomial series, which is 1 plus x to the negative 2. There we got the final expansion. Now we will come to the real task. We need to represent this binomial expression as a power series. How are we going to do this? Can I write that it equals to summation of n plus 1 into x to the n into negative 1 to the n, where n starts from 0 up to positive infinity. Look, it is the equation of the power series. It is my power series. Because remember, this n plus 1 into negative 1 to the n is my a sub n, and this is my x to the n. It is the equation of the power series, which is a sub n into x to the n. For the a sub n, I have n plus 1 into negative 1 to the n. Suppose n plus 1 into negative 1 to the n is my a sub n. So these terms are exactly the summation of this stuff. When you start from n equals to 0 and plug in different n values, you will get the same terms. So we can say that we represent the binomial series as a power series. Now make sure you have to do this by yourself. You have to look to the binomial terms. Based on these terms, you have to make a sub n by yourself, which I did it here. Now you might be confused that what is the logic? It is complicated. How are we going to know that we should put n plus 1 into negative 1 to the n? You have to look to 2 things. The first thing is you have to check the coefficient. If you look to the coefficient, we have 1 and then 2 and then 3 and then 4, which means that the coefficient of each term increases by 1. Like first we have 1 and then 1 plus 1 2 and then 2 plus 1 3 and then 3 plus 1 4 and then 4 plus 1 5. Therefore, if I use term n plus 1, is it okay? Yes. Because look, at n equals to 0, if I plug in n equals to 0, I will have 0 plus 1. 0 plus 1 is 1. So I will get the first coefficient. And then at n equals to 1, if I plug in n equals to 1, I will have 1 plus 1. 1 plus 1 is 2. I got the second coefficient. At n equals to 2, just plug in n equals to 2 here, I will have 2 plus 1, which is 3. I got the third coefficient. At n equals to 3, when I plug in n equals to 3 here, I will have 3 plus 1. 3 plus 1 is 4. I got the fourth coefficient. And similarly, at n equals to 4, I will get the fifth coefficient and the sixth and the seventh. So it increases by 1. Therefore, I can put n plus 1. This is the first thing that you have to look to the binomial terms. The second thing is that you have to look to the sign. If they have alternate signs like positive, negative, positive, negative, positive, negative, then you have to use negative 1 to the n. You just directly put negative 1 to the n, because only then the alternate signs will be possible if you put negative 1 to the n. If the value of n is even, you're going to have positive value. If it is odd, you're going to have negative value. The third thing is that you have to look to the power of variables. Here the power of x is 0, but normally we don't write x to the 0 because x to the 0 is 1. There is actually x to the 0. So we have x to the 0 here, and then x to the 1, and then x to the 2, and then x to the 3, plus x to the 4, plus x to the 5, up to infinity. Which means that the power of x is in ascending order towards the right side. 0, 1, 2, 3. Therefore, I can simply put x to the n, because at n equals to 0, I will have x to the 0, which is for the first term. At n equals to 1, I will have x to the 1, which is for the second term. At n equals to 2, I will have x to the 2, which is for the third term. At n equals to 3, I will have x to the 3, which is for the fourth term. At n equals to 4, I will have x to the 4, which will be for the fifth term, and so on, up to infinity. Similarly, to know the alternate sign, at n equals to 0, I will have negative 1 to the 0. Negative 1 to the 0 is 1. So I will have positive sign here. At n equals to 1, just plug in n equals to 1, I will have negative 1 to the 1. Negative 1 to the 1 is negative. Therefore, I have negative in front of the second term at n equals to 1. At n equals to 2, when I plug in n equals to 2, negative 1 to the 2 is positive. Therefore, I have positive sign. At n equals to 3, when I plugged n equals to 3 here, negative 1 to the 3 is negative. Therefore, I have negative in front of the fourth term, and so on. So if n is even or 0, then we will have positive sign. If n is odd, like 1, 3, 5, 7, then the sign will be negative. These are the three areas that you have to look to the terms. You have to make the power series by yourself. Now let me plug in random values for the n, just to know that whether I can get the exact thing or not. So by plugging n equals to 0 here, just plug in n equals to 0 here, n equals to 0, and n equals to 0. So 0 plus 1 is 1, and x to the 0 is 1, negative 1 to the 0 is 1. So 1 times 1 times 1 is 1. Therefore, I have 1 for the first term. At n equals to 1, just plug in n equals to 1 here. 1 here, 1 here, and 1 here. So 1 plus 1 is 2. X to the 1 is x. Negative 1 to the 1 is negative. So negative times 1 times 2 will be negative 2. So 2 times x will be 2x, but then I have negative. It will become negative 2x. At n equals to 2, just plug in n equals to 2 here, 2 here, and 2 here. 2 plus 1 is 3. X to the 2 is x squared. Negative 1 to the 2, which is even, 2 is even, will be positive. It equals to positive 1. So positive 1 times x squared is x squared, and then times 3 will be positive 3x squared. Similarly, at n equals to 3, just plug in n equals to 3 here, and 3 here. 3 plus 1 is 4. X to the 3 is 3. Negative 1 to the 3 is negative 1 because n is odd, 3 is odd. So negative 1 to the 3 is negative 1. Negative 1 times x cubed times 4 will be negative 4x cubed plus infinity. You can go up to infinity because remember, from 0 and then it goes to infinity. It is actually the infinite binomial series. Therefore, we can represent it as a power series. Remember, you cannot represent the finite binomial series as a power series. It must be infinite. Then you can represent it as a power series. Because actually power series is an infinite series. So we need something infinite in the binomial as well, which is only possible when the power n is in negative form or in fractional form. Just to remind you one thing here, that look, I have 1 factorial here and 0 factorial for the first term. But since 0 factorial equals to 1 and 1 factorial equals to 1, therefore normally we don't write 0 factorial for the first term and 1 factorial for the second term. In real scenario, we have actually 0 factorial here and 1 factorial. 0 factorial, 1 factorial, 2 factorial, 3 factorial, up to infinity. So there we represented the binomial series as a power series.